Hello everyone, today I'm going to talk about PETAce, which is TikTok's first open source framework for cryptography and privacy enhancing technologies, and this project is open sourced in GitHub. With the development of artificial intelligence, we are now living in the era of big data. Data is very helpful, and data analysis can help with a lot of different tasks. For example, it can help with the decision making, understanding patterns, improving efficiency, driving innovation, and risk management. And on the other side, people's awareness of data privacy has also increased significantly. So if you know, we a lot of regions published their privacy regulations. For example, in Europe, they published GDPR, and there is CCPA for California as well, and there are a lot of other privacy regulations in different regions. And if you notice, actually, now the operating system also take more care to the user data privacy. Now, if you want to install some software in your mobile phone, usually the system will pop notifications checking whether you want to share your user data with the app developer. So these are all good signs to show that people are paying more attention to their data privacy as of now. But one situation is that many use cases in data analysis actually require the data from multiple parties and thus raising privacy concern. Since usually the situation is the data itself might be sensitive. For example, in healthcare research, let's say we have a lot of hospitals, they may want to use their patient data to train some model, and the thing is the patient data is highly sensitive. It can directly infer someone's health condition. So if the hospital simply just share this patient information with each other, it directly violates the user data privacy. So in this case, what we can do is basically we need to use some privacy enhancing technologies here to finish this computation task while preserving the user data privacy. So there are also other similar examples such as ads management and financial data analysis. The data involved here are all highly sensitive, so we do need some privacy preserving method to do this analysis. In today's talk, we are going to give a very concrete example, which is ads measurement, to show you how privacy enhancing technologies can help here. So in this scenario, we have two parties. One is the advertiser, the other is the publisher. So the task is that the advertiser wants to launch ads campaign on the publisher side, and the advertiser wants to know the outcome. So in real cases, the publisher could be some social media platforms such as Facebook or TikTok. They have a lot of user base, and so the publisher can just produce the advertisement and forward the advertisement to the users, so that a lot of users can see this advertisement. And fortunately, after the users see the advertisement, if they think the product is good, they may go to the advertiser's website and make the purchase. And here, the ads measurements the goal of ads measurement here is to measure how much money were earned through these ads campaign. And if we abstract this problem a little bit, we can think of it this way, like we have two parties here, each of them have their own database. So on the publisher side, there is a database containing some user IDs and the impression time. So user IDs are basically the users who saw the advertisement, and the impression time is the time that they saw the advertisement. And on the other side, there is a database belonging to the advertiser as well. So there are three columns here. The ID is the ID of users who make the purchase, and the conversion time is the time that they made the purchase. And of course, the value here is the money spent. If they have these two tables together, actually the logic of ads measurement is straightforward, since we want to find some users who both see the advertisement and make the purchase. So the idea is we simply join two tables using the ID column as the key, and we will get this table here. Then we just need to check if there exists some user whose conversion time is later than the impression time, since it only makes sense if a user first see the ads, then make the purchase. If the order is reversed, then it definitely is not because of this ads campaign. So if this time condition is satisfied, we simply add the value to the final result, and we check this row by row. Finally, we will get the total conversion amount. So as we see, if everything is computed in plain text, this is very straightforward and simple. And this is usually what happened before 2017, when people are paying almost no attention on the data privacy. So this computation, all the information here can be easily available through some third-party cookies, and the accuracy is even better. But the situation here is that if we simply just do this compilation in plain text, you see there's some privacy violation, of course, since the advertiser side, they may see some extra information that is not necessary for the ads measurement, but it's actually some private user information. For example, the advertiser may just see how many users watched the advertisement, and how they can also figure out which user did not see the advertisement. So these are all extra information and might be valuable commercial-wise. So right now, what we want to show here is an evolution of the ads measurement. So here you see in this figure we have two axes. The x-axis is the utility, which means how accurate the ads measurement could be. And on the y-axis we have the privacy, basically meaning that how much the privacy is preserved for user data. And in the year 2017 and before, we are in this checkpoint 1, where the utility is maximized because everything is computed in plain text, and also we can rely on some features such as cross-web tracking to get even more accurate result. So at the same time, the privacy is minimized because there is basically no privacy. Both the publisher and the advertiser learns extra information about the other side. So this is indeed bad for privacy. Then as the time goes to the 2020, as we see, there are more privacy regulations and people are paying more attention to privacy. So the original method, which is to compute everything in plain text, is no longer available. So we see the utility directly drop to almost 0. And also another factor is that at the year of 2020, a lot of restrictions are also applied on the cross-app tracking, for example, third-party cookies. So all of these reasons, finally, we have basically the previous solutions does not work anymore. Then as time goes, many companies decided to build their own solutions based on privacy-enhancing technologies. So the idea is we can do this computation actually in some confidential form so that the user data is never revealed to the other party, and meanwhile we can also do this computation meaningfully. But you see the utility is still worse, but the privacy has increased. So this is the checkpoint 3, and now we are in the checkpoint 4. So what we want to see here is that we want to achieve the best of the two worlds. We want to achieve the best trade-off between the utility and the privacy. And when we see the privacy here, we actually means the privacy for both sides. For example, the advertiser should not track any user behavior on the publisher. For example, the advertiser should not check whether a user see advertisement on the publisher side, and also advertiser should not have any information about when did the user see the advertisement, since these are kind of sensitive information on the publisher side, which can directly give you some idea about the user behavior, right? So this is the privacy on the publisher side, and on the advertiser side, the privacy is also defined for publisher. So the publisher should have no idea about any purchase behavior on the advertiser side. So this privacy is symmetric to two parties. And also, meanwhile, we want to achieve somehow better utility here. The utility, of course, will not be better than the plain text version, since you have to sacrifice some accuracy for privacy protection, but we want to achieve that like the best as we can. So this is the general timeline about the edge measurement, and what we want to show here is actually privacy enhancing technology can help in this situation. So privacy enhancing technology is a very broad concept. It guarantees privacy through using a lot of different measurements, such as cryptography solutions or math solutions. So they can be as easy as encryptions or cryptographic hash functions. So these are actually the fundamental building blocks, and maybe you don't notice, but you actually use it every day when you are using internet. And there are also more complicated protocols such as secure multi-party computation. They can help with more complex computation tasks while preserving each party's data privacy. And meanwhile, we also have hardware-based solutions such as secure execution environment, and there are also purely mathematical-based approaches such as differential privacy. So they are all privacy-enhancing technologies, or we will call it PETace for the rest of this talk. They can help with different scenarios, like to satisfy different privacy requirements. Then we are going to talk about PETace. So we want the PETace to be a one-stop solution for crypto and privacy-enhancing technologies. So here we want to provide plenty of cryptographic primitives and some high-level protocols, and also a general-purpose secure multi-party protocol framework. So the goal is we want to provide a complete toolchain for people with different backgrounds. In general, we provide 4 kinds of protocols in this framework, and the target user are different for each category. So on the first layer, we have cryptographic primitives such as AES, pseudorandom generator, cryptographic hash, homomorphic encryption, and elliptic curve operations. So as you see, these are actually all the fundamental building blocks for the crypto protocols, and the target user is academic researchers or engineers who want to build their own protocols from scratch. And as you know, implementing cryptographic protocols correctly is actually more challenging than you thought. There are a lot of different risks and other set channel attacks which you may not notice if you just decided to, let's say, implement some AES on your own. So we will provide these primitives, and you can use these secure implementations to build protocols on your own. So this is the first layer, and on the second layer, we have some two-party protocols like oblivious transfer and oblivious PRF. So these are the fundamental protocols for two-party interaction, where the privacy-preserving computation may require two parties to exchange data with each other. And also on the third category, we have two-party computation. So we provide a general-purpose two-party computation framework. And this includes state-of-the-art protocols for a lot of different operations, such as secure comparison and other nonlinear functionalities. We also support homomorphic encryptions here. And in the future, we also plan to put more of our innovations into this framework as well. And engineering-wise, it is also optimized. So it achieves a very good performance. And on the last layer, we also have specialized two-party protocols, since we realized that, especially in industry, there are several multi-party computation protocols that are widely used in many situations. One of the good examples is private set intersection. They can help a lot of different scenarios. And also the other protocol is privacy information retrieval. So we provide these specialized protocols so that if your scenarios fit the requirement here, you can directly use it. And this is the general architecture here. As you see on the bottom layer, we have all these cryptographic primitives. And on the second layer is that are actually a lot of two-party protocols. And we had planned on three-party protocols, but it's still in progress. So these two-party protocols actually use the cryptographic primitive as building blocks. And on the upper layer, which is the application layer, we do want our protocols to be friendly for users to use. So here we actually provide a Python interface for our general purpose multi-party framework. So the idea is that the user, if they're not familiar with what is secure multi-party computation, what is crypto, they can still use the friendly Python interface to finish some coding for the privacy-preserving applications. For the Python interface, it's like we have this structure of the virtual machine. So we also have a compiler which will compile the corresponding Python code into instruction code, and the virtual machine will run these instructions with the underlying MPC framework. So here we want to show a simple example of how to use this Python interface. On the left-hand side, this is a plain text computation where you just use the NumPy library in Python and you do a linear regression, which is basically an inner product of two vectors. So the coding is pretty simple here. And on the right hand, we have the same computation using our Python interface. Of course, you need to import the libraries, the PETAce libraries. And also, since this is a multi-party protocol where you need internet interaction and you need to initialize our MPC engine, so you have some other extra codes here for network, and also you need to set the data. You need to decide which data is private that you do not want to share with the other party. But after all this setup, actually the rest of the computation is almost the same as the plain text version. So you see this is quite user-friendly. And after introducing the PETAce functionality, we can see what it can do. One of the PETAce applications is exactly the as measurement that we just introduced before. As you see, the computation logic of as measurement is actually we want to join two tables using the ID column here. And this is exactly fits the concept of private set intersection, and it is supported by PETAce. So what we can do is we can first use private set intersection protocol, or PSI, to merge these two tables, find the intersection, and then for each record in the intersection, we can use general purpose two-party computation protocols to decide whether the conversion time is larger than the impression time. If that's the case, we will add this value to the final result. So you see, PETAce can help with the end-to-end execution of as measurement, and the guarantee is that no party will know any information about the other party's data. So this is one application of PETAce. And another application of PETAce is actually contact matching. So the contact matching is basically like TikTok can help you find whether your friends in your contact list also use TikTok. If that's the case, TikTok can forward them to your friends. So the process, obviously, this can help a lot with the user growth, and user experience also can be improved significantly since it's a social media platform and you can have more friends. But there is also a disadvantage, because if we directly ask the users to send their contact information to the TikTok, this is a violation of user data privacy. So what we can do here is we can also use the private set intersection protocol. Since here we also have two parties, the user and the TikTok, and the users have a database which is their contact list, and the TikTok has a database about its users. So if we join these two data sets together, we will see which user are both this user's friend and also use TikTok. So as we see, the PSI functionality can perfectly solve this problem while preserving all the privacy. So this is in general what we want to show for privacy, and this is a takeaway. We want to show you that the PETAce actually provides a completed toolchains if you want to build your own PET applications, and we have different protocols to suit different needs. If you're an academic researcher, you want to build everything from scratch, we have all the crypto primitives as fundamental building blocks. Or if you just want to try some high-level applications such as PSI, we have that integrated as well. And also, PETAce is friendly to use for people with different expertise. So as we just mentioned, people with different background can also find a meaningful way to use PETAce. Also, PETAce now is open sourced in GitHub, and it welcomes contribution. We want you to, any collaborations are welcome. Feel free to let us know if you want to contribute, and let's make it better together. Thanks.